a big new push for quantum information throughout throughout the US. The goal is to try and sort of move this important field forward past where it's been. And so a number of new centers have been stood up, and ours is launched out of Brookhaven, and it's centered around this idea of co-design. Um, sorry. Okay, the team consists of people at now 18 universities, 4 other federal labs besides Brookhaven, Brookhaven itself, and IBM as our main corporate partner. But you can see that that we have folks who are scattered all around the US, and our goal is really to try and sort of push quantum information processing, generally speaking, into some real compelling economic and technological effort that actually bears fruit. And so, this is a thing that for me personally has been exciting. I feel like I first saw the very first superconducting qubit right as I was graduating college, and so this has sort of been a thing that essentially has been happening my entire adult life, and so it's been really exciting to watch it and be a part of it. And if you think back, to where we are now, right? If you read the news, you'll see articles about, quantum supremacy from Google or this new breakthrough from IBM. There are really exciting developments that had their origins, a decade ago, from many of the people who are part of C2QA, where some of the very first algorithms were ever done on a chip at Yale, the kinds of qubits and all of the components that you see in these commercial processors were sort of developed, 10 to 20 years ago in academic labs. And what's happening now is what we call the NISQ era of quantum information processing. So it's the noisy intermediate scale quantum era. And in this era, the idea is that we have, qubits that can, computers that can have 50 qubits. You can have enough parts to do something a little bit interesting. We don't yet have good enough parts that we can do error correction. And so we're really sort of in this intermediate scale where we're trying to do things as well as we possibly can. The goal of our center is to try and build the bridge that allows us to get to the post-NISQ era. That allows us to do error correction. It allows us to do fault-tolerant processing. It allows us to do scalable distributed communications and all of these kinds of things that you would really need in order to actually have a robust quantum era where real useful technologies can come out of this. And so the goal of the center is to try and push us past that point. What's different about a center focus compared to what you can do in individual things? Well, I would say the real goal of the center is to try and bring together an enormous number of talented people who have talent in different areas of this enterprise, right? Quantum information is a fun field because it's incredibly multidisciplinary. We have people who really know a lot about materials. You have to know a lot about devices. You have to know a lot about underlying physics. You also have to know about software and applications and computer architecture. And no one person really knows all of those things absolutely perfectly. And so what we have is we have a center where we are trying to bring together scientists with different areas of expertise and find ways for them to work together, and not just to work together, but to really try and design a larger system, to think about a larger system using all of their expertise. Because oftentimes you will make decisions in one area of this sort of large technological stack that have implications for the others, and you don't even know what you're doing. And so we're trying to find out what are the mechanisms that we can communicate to each other if we don't speak the same language, right? Computer scientists and physicists and material scientists, all trying to sort of use what they know and find out what the problems are in other areas. We've broadly sort of sorted our interests into 3 thrusts. So there's this green thrust, which is the materials thrust, which is really trying to think about what are the materials components for quantum information processing. What do you make this stuff out of? What are the coherence properties of those materials? Are they good enough? Can we make them better? There's the device side of this, which is now you sculpt those materials into different structures, and you try and use those structures to embed quantum information to have it last a long time. And exactly how you do that matters quite a bit. It might make certain problems easier. It might make certain problems harder. And so that matters quite a bit. And then finally, we want to try and think about the application side of this. So now, suppose you have 50 qubits and you put them together. What can you actually do with them? Can we develop sort of new methods of new algorithms and new things that we can run on our software? Can we find more efficient ways to run software on a fewer number of qubits? The big sort of banner goal of the center is what we call the 10-10-10 improvement. So the goal is to really figure out how to get 10x improvements in all three of these areas, and not just in all three of these areas, but in all three of these areas in a way that we really hope are compatible, right? So one challenge in all of this is that sometimes you can maybe get a 10x improvement in your device, but it doesn't, it doesn't translate well to a particular architecture, or it's made, or you can get a 10x improvement in materials, but you can't, integrate those easily into devices, and so it doesn't really help with this sort of, across the entire stack. And so the goal is to try and not just find these improvements, but it's to find these improvements in a way that can sort of break out of their silos and work together across different thrusts. And so I'm going to sort of spend most of the time talking not about the structure of the center, which is, a center, but about some of the work that's been going on in my group on superconducting qubits, trying to put it into a little bit of a historical context, and then think about how that sort of is emblematic of the kinds of things we're trying to do as part of this center. And in particular, most of my work falls under this sort of green and orange sections of the pie. It's really thinking about materials and devices, and trying to get improvements in materials and devices, and showing how sort of different approaches can get to where you want to be. So in the end, the goal, at least the goal that I'm sort of narrowly going to talk about, is trying to make qubits that are more coherent, trying to make qubits that can store information that can last a longer bit of time, and think about how we can actually go about doing that. Okay. And really, that's trying to think about what we like to call next generation superconducting qubits. So, we've now had 22 years of superconducting qubits. So the very first superconducting qubit was demonstrated in 1999. So it's been 22 years. But for the last 15 or so years, most people have been using one particular qubit called the transmon. And so I want to talk a little bit about how we got to the transmon and how we use superconducting circuits to encode quantum information, and then a little bit about what we might want going forward if we're going to try and get 10x improvements in a superconducting qubit. Okay. So sort of broadly speaking, and this is now going way back to the beginning, I would say when we're thinking about quantum computing and storing quantum information, we're really trying to think about the 21st century version of quantum machines. And so Rob Sholkoff made this slide originally back when I was a postdoc for him, and it really points out that the vast majority of technological development in the 20th century relied on two devices, relied on a CMOS transistor and a laser. And these devices don't exist if you don't have quantum mechanics, right? If you don't understand the discreteness of energy levels, you can't make a laser. If you don't understand band structure, you certainly can't make a transistor. And so the parameters of these devices, the way they work is entirely determined by quantum mechanics. And without those, communication and computation and sensing would all be vastly, vastly different. There is no way that I could be sort of sitting at my house here in New Jersey on a computer that is sort of sending out my talk to you wherever you happen to be, right? That relies on computing power and it relies on lasers for communication. So much of what we do is touched by those devices, but in their everyday operation, those devices are actually very classical, right? The transistor is either on or off. It's not going to be in a superposition state. It's not going to be exhibiting any of the sort of weird aspects of quantum mechanics. A laser is going to be outputting a coherent state of light, sort of one of the most classical states of light. You're not going to be thinking about sort of entanglement and all of this kind of stuff in the sort of everyday operation of a laser. And so the goals of our center is to go beyond this sort of this and think about how you can actually encode information in not just understanding how a particular thing works, but in actually how it operates. And to do that, we want to encode information in some kind of system. And some of the very first qubits people ever built were spins. Spins are great if you want to build a bit, which is a two-level system, because spins are very naturally two-level systems. And so they work well. I work in a field that uses superconducting circuits in order to encode quantum information. And so the question is, how are you going to actually go about doing that? And why would you use superconductors? And the first thing I would say is superconductors give you one incredibly magical property, which is that when you make them cold, okay, first of all, they give you the property, which is that they're really good conductors. And so you don't get a lot of dissipation. And that's really, really useful in terms of not having errors and not having energy sucked out of your system. But they actually give you another thing, which is incredibly useful, which is they give you a very, very, very well-defined ground state. And so if you take a metal and you cool it low enough and it's a superconductor, then a gap opens up and a well-defined ground state emerges. And you can use this as like a zero logical state to store absolutely no information whatsoever. But if you then try and impose some kind of structure, then you might be able to actually build a qubit. So the idea is, a normal metal has so many low-lying energy levels that it's sort of hard to think about having a true ground state. Whereas the gap in a superconductor allows you to have a true ground state. And so we can think about structuring the metal into some kind of circuit in a way that actually gives you something that looks like a qubit, something that has sort of discrete energy levels that you can access. And if I'm trying to think about this, if you sort of say, well, I have a superconductor and I want to sort of build it into some circuit, and I want it to have a circuit that has some well-known energy or some well-known frequency to it. But the first thing that comes to mind is to build an LC circuit, right? Because an LC circuit is a harmonic oscillator, it is a resonant circuit. It has a well-defined energy and frequency. And so if you take a superconductor and you shape it into an LC circuit, then you've realized something that actually does have discrete energy levels. The problem is that the discrete energy levels are perfectly harmonically spaced. And so you can't uniquely address a 0 level and a 1 level without having to worry about the 2 level and 3 level and 4 level and 5 level. And so you need something a little bit more than an LC circuit. And that's the other thing that you get really nicely from superconductors, which is you get this device called a Josephson junction, which is formed by making a metal insulator metal sandwich. And it's something that you can think of sort of like a nonlinear inductor. And if you have a very strongly nonlinear inductor, then you get a potential now that is almost like a harmonic oscillator, but a little bit softened. And because it's a little bit softened, it allows you to have slightly different energies for your 0, 1, 2, 3, and 4 state. And it allows you to sort of use frequency to isolate 2 levels, the 0 state and the 1 state, and call those the logical states of your qubit. And when you get energy levels that are anharmonic enough to be used in this way, we call it an artificial atom, because the world really only has like harmonic oscillators and anharmonic oscillators, which are more or less like photons and atoms. And so we're making artificial atoms by patterning superconducting circuits. This graph from 2013 shows an enormous rate of progress in the coherence time of superconducting qubits. This is how long you can store information in a superconducting qubit if you know the very first qubit was sort of down at the nanosecond level, and gradually over the years people figured out either new designs or new materials which sort of push this up and up and up to the sort of present day, which is where we get qubits that are on this sort of tens to maybe 100 microsecond regularly, or at least that's sort of where we were a year ago. But you'll notice it's also where we were in 2013. So I want to give a little bit of a history and talk about how we sort of moved up this curve and the kinds of approaches you could use to move up this curve before we start thinking about where we might go from here. And I'll try and do this very briefly. So the very first qubit was from 1999. It had these sort of big, beautiful purple waves. This qubit was known as the Cooper pair box. It was first done as a qubit by Yasu Nakamura. There was a big conference 2 years ago where we celebrated 20 years of superconducting qubits. And the idea here is that there is a tiny piece of superconductor, which is called the box, and it's coupled to the outside world through these Josephson junctions. And if you apply a gate voltage to it, if you sort of bias this capacitance with its capacitance to the rest of the world, then you can get to a point where there's sort of it's equally happy to have sort of n equals 0 or n equals 1 Cooper pairs on that box. So there's some sort of significant energy cost to adding even one extra Cooper pair to that box because of its capacitance. And if you sort of move to this point where an extra Cooper pair wants to tunnel on and off, you wind up producing these superposition states where you have sort of even and odd superpositions of the number of Cooper pairs on the box. And if you can move in and out of this point really, really quickly, then you can cause oscillations in the state of the qubit. That is, you can sort of move to a point where you have sort of n equals 0 Cooper pairs. You can move in really quickly, and if you do it non-adiabatically, then you're not in an energy eigenstate of the system, so you get oscillations and you can move out. And if you can move in and out and control this voltage on a picosecond timescale, then you can see these oscillations. And these oscillations are really the telltale sign that you have a qubit. These are the sort of coherent oscillations of a Cooper pair onto and off of this island. The problem in this picture is charge noise. It turns out that that if you sort of have a qubit where you have energy levels that are sort of sitting here at some particular point in your applied gate voltage or your gate charge, then if you were able to hold that voltage absolutely perfectly steady, then there would not be a whole lot of noise. The energy difference between your 0 state and your 1 state would be incredibly well defined, and a superposition of those states would last for a long time because the energy difference tells you about the time evolution. And if that energy difference is unstable, then the phase that you accumulate in time is unstable, and your information will very, very, very rapidly dephase. And if you sort of move at this point, then if in reality, there's sort of material defects that are going to be moving around and causing some fluctuation in the electrostatic environment. And that's going to cause like your bias point to wiggle up and down. And that's going to cause dephasing. It's going to cause your quantum information to get destroyed. If instead of sort of operating on the sidewall of this sort of red and black curve, if you move to the this charge degeneracy point, the point where the first derivative is 0, then you are to first order protected against charge. And this was the quantronium experiment from Michel Devereux. If you do that, in the typical devices around 2005, people saw T1s of a few microseconds and T2s that were 500 nanoseconds, which is 500 times bigger than the first qubit that was ever made. But here still, you are limited by higher orders of charge noise. So even though if you're sitting at this bias point, you're first order protected against charge noise, you still sort of experience the curvature of this band a little bit, and your T2 is still limited by charge noise. So you can, that slide went missing. What can happen, and I don't know why that slide is gone, that's weird, is if you increase the capacitance between this box, if you shunt this device with a capacitance, these bands flatten out more and more and more. And when that happens, you essentially get a device where there's absolutely no remaining curvature in the band. And in that case, you just are utterly insensitive to charge noise, right? So this sort of shows that you can take a device and you can not actually fix the underlying problem, right? Nothing here has gotten rid of whatever it is that's causing the noise and the voltage or the charge that you don't have control of. It's finding out what is limiting your device and rendering your device less sensitive to that noise channel. Alternatively, you could also have figured out what the underlying noise problem was and just gotten rid of all charge noise. And in some sense, this is the kind of choices that you have available to you. If you want to move beyond where we are in coherence and in the quality of these systems, you either need to figure out how to get rid of these wiggles by making charge noise better, or you need to figure out how to make your qubit immune to that source of wiggling, but not just for that source of wiggling, but for whatever the current limit of noise on your device performance is. So I showed this graph at the start, which is my favorite graph because it cuts off in 2013, which is about when this exponential Moore's law like growth and the coherence of qubits stopped. The more recent graph from also produced by Will Oliver, sort of you can see it starts to roll off starting around 2013. And then there's some points up here which maybe get up to a millisecond, but these are not the coherence time for qubits. These are like the coherence time for 3D cavities that are sort of metal boxes which can't be controlled in the same way. And so you really start to see that the progress in the lifetime of quantum information has stalled. That doesn't mean that quantum computing progress has stalled. And if you think back what's happened in the decade, amazing things have happened. People have done, these great simulations of material systems, and Google has its announcement that it can do something on their computer that can't be simulated on a classical computer. So there has been scaling, not in the coherence of qubits, but in the complexity of systems that we can build and the number of qubits, which is great. But the qubits themselves are not yet good enough to move beyond the NISQ era of quantum computing. That is, that they are not yet good enough that we can correct errors faster than errors creep in. And so we need at least another factor of 10 in qubit coherence and other factors of 10 elsewhere in order to make these systems better. Now, how are we going to do that? How do we move beyond this? And so I like to always sort of think about this as following the golden rule, right? So here I've put up some version of Fermi's golden rule, which talks about some decay rate in a problem. And right now, the thing that is limiting transmon qubits, which is the qubit that everyone uses, is relaxation. It's sort of it's energy leaking out of the system. And if I look at this and I'm a thorough scientist, and I say, well, I want this rate of energy decay to be small. So what could I possibly do to make this rate of energy decay small? Well, I can't change 2 or bar or H bar. So basically, all I can do is either engineer this matrix element to be small or change the environmental noise to be small. And if we think about this in the sort of picture of the C2QA center, one of these approaches is really the devices approach. I can engineer a device where this matrix element is small, and another is a materials approach. I can sort of think about what's in my environment that might be causing relaxation, and I can do some materials engineering to make that small. And so these are sort of how these two thrusts kind of work together and play off each other. So how could a device make this small? Well, we've made this transmon, which is basically this capacitively shunted Josephson junction, and we got rid of our charge noise by making the potential really shallow, which distributes the charge. It delocalizes the charge. It sort of spreads it out over a number of possible charge states, and that delocalization is really the origin of the protection against charge noise. We could similarly have not an island with a capacitor, but we could shunt the junction with an inductance. And then instead of an island, you get a loop. And that's sensitive not to charge noise, but to flux noise. And similarly, if you distribute your state over many flux quanta, then you wind up with a strong insensitivity against flux noise. And so if we think about this dephasing picture, the one I started the talk with, we really like to have systems that are delocalized, because that allows you in your phase space picture, because that allows you to get protection from your noise sources, protection from dephasing to many orders. The challenge is that this is sort of the opposite of what you want to have for relaxation effects, right? So if in this picture, if we want to have T1 be long, the problem in the transmon, and this is the transmon picture, is that these energy levels have significant overlap in phase space, and the matrix element that drives relaxation is always quite large, and there's nothing you can do to make this large. There's always an ability to have energy relax from the 1 state down to the 0 state. It is possible to make a qubit, and that's the one I have in the middle here. It's possible to make a qubit that in fact has very little, very small matrix elements. So in this picture I drew in the middle, this is sort of some potential in flux space. And if my 0 logical state were here and my 1 logical state were in a completely different well of this potential, then any local matrix element is going to be small, because these states are disjointly supported. That is, one of these states is non-zero whenever the other one is 0, but sort of if you multiply this with any local matrix element and integrate, you're going to get a really small matrix element. And so the good news for this state is that T1, the time scale that governs relaxation, would be incredibly long, but T2 is going to be incredibly short, because each of our wave functions is very hyper localized. And so, and we said we sort of protect against dephasing, we protect against T2 type errors by delocalizing. You could sort of spread out your quantum information across many wells, like I show on the right picture here, and then you have good T2, but your T1 is bad. In the charge mode, we don't actually have a way to make a good double well potential, but your T2, if you delocalize over many charge states, is spread out really nicely. And so if you have these single mode qubits, you have this challenge, which is that you kind of want your information in some phase space picture to be very localized, because that allows you to get long T1, but also very delocalized, because that allows you to get long T2. And you can't really do both of those at the same time. And so the goal is then to think about a more complicated superconducting qubit, or one that might have different components than we have available to us now, that could do better. And in particular, this involves these things called 0 pi junctions. And so the idea is to provide both disjoint support and protect against dephasing. And it starts with this sort of wishful thinking perspective, right? So we have this this device called a Josephson junction, which has a potential which goes as the cosine of the phase difference across the potential. It gives us this cosine potential we've been using, which is great. If we had something where it wasn't Cooper pairs that tunnel, but pairs of Cooper pairs that tunnel, then the potential would naturally be a double well potential, and yet it would be robust against noise because you could spread out over many charge states within each well. So this potential could be a thing that could be very useful, but we don't actually have a device that allows us to have pairs of Cooper pairs tunnel. And there have been a whole number of proposals sort of thinking about ways that you might actually be able to do this. And we've sort of based ours on this design by Brooks, Katayev, and Preskel called the zero pi circuit. And the idea is it's sort of a way that allows you to get something that effectively simulates pairs of Cooper pairs tunneling. The idea of how it works is that you have a circuit that looks like this. So now it has 4 nodes, which are the 4 corners of this square. It has 2 Josephson junctions, 2 capacitors, and 2 inductors. Now, the inductors have to be really, really, really large, which make these connections, these inductive connections, have a very, very high impedance. And the capacitors have to be quite large, which means that these connections have a very low impedance. And there has to be no parasitic things anywhere else that are going to sort of mess up this impedance picture. And if that happens, then if you have a tunneling event from this top left part of the square to the bottom left part of the square, if you have a Cooper pair tunnel, then that leaves some positive charge on this sort of brownish part of the capacitor. And you'll want some extra negative charge on this bluish part of that capacitor. But where is that charge going to come from? Well, if the inductors weren't there, you would just sort of have charge move over and sort of and happily be on the other side of the capacitor. But because the inductors have such high impedance, the sort of fastest path, the easiest path to sort of balance the charge on this capacitor is to have another Cooper pair tunnel from the top right of the box to the top left of the box. That way you have sort of positive and negative charge on the sort of opposite parts of this capacitor. And so in order to get this sort of picture to work, what happens is that if one Cooper pair tunnels from the top to the bottom, a second has to tunnel from the top to the bottom. And if you think of this sort of like this collective top half of the box and the collective bottom half of the box as one entity, then it's something that effectively looks like the 4 electron, the pair of Cooper pair tunneling that we want. And so that's the kind of thing that we want to build. Now, it's more complicated than that because there are other internal degrees of freedom. If there are 4 nodes in the circuit, there's going to be 3 modes of the circuit. And so it will have other resonant modes that you have to avoid exciting. It will also have lots of other ways that like that this circuit could break down if you have parasitic capacitances and things like that. But that's essentially the picture we're trying to go for, because that gives us something that allows us to have the information localized in each of 2 wells and still be robust against dephasing. So it gives us an intrinsic protection against T1, something that comes not because you've made the materials better, but because fundamentally that matrix element is small and that transition is hard to drive, and T2 is good. So it turns out the full potential, if you think about all of the degrees of freedom involved with the problem, looks more like this sort of funny corrugated thing where the 2 wells we're talking about are in this theta axis, but there's also some sort of more structure going on in the phi axis, which is one that has an actual loop. In principle, if you make these inductors large enough, then you get something that really very much looks like that sort of idealized 0 pi system. We don't yet know how to make that. And so we're doing something that is a crude approximation of that, which is getting sort of close and allows us to see at least some of the behavior that we would like to see. And in this potential, you can see the ground state of the system is this sort of orangish blob that's in the 0 well. The first excited state of the system exists in this opposite well, and yet has at least first order protection against all kinds of dephasing. If you actually draw out all of the energy level, all of the energy levels of the system, you can see here's the ground state I showed you, and here's the sort of first excited state and its sort of twin paired state over here. And there's all of these different states which you can label just like you would actual atomic spectra, where you can think about the number of nodes in each search and in each well, and the orientation of the nodes in each well, and the parity of the well, and you can really sort of get this very rich picture of what all of these wave functions look like, and they look a lot more like atomic orbitals. And so so rather than just having an artificial atom where it's an atom because it's not harmonic, we actually have something that's more like an artificial atom because there are selection rules and really a sort of rich internal structure to the electronic states. If you make this thing, you know, we pattern it out of superconducting materials. This one was patterned out of aluminum. We now make them out, patterned out of niobium with aluminum junctions. We now pattern them out of tantalum and aluminum junctions, and I'll get to that part. You can see I've sort of color coded the circuit diagram, which shows where all the inductors, capacitors, and Josephson junctions are. Or at least where the metal is. So the capacitors are these toothy structures at the top and bottom. These long silver structures are arrays of Josephson junctions, which act like large inductors. And then sort of going from red to green and blue to yellow here, you can see the single Josephson junctions. When you make this structure, you can then put it inside of a dilution refrigerator and cool it down to 10 or so millikelvin in temperature to get rid of all of your thermal excitations. And you can probe the spectrum of this with a spectroscopy technique, and you can see there are many lines here. But if we fit them carefully, you can see that they match amazingly well with the theory of this very complicated potential. And in particular, we can then extract from the data where these are, and you can see all of the dots fall along the lines where we expect them to be, with one problem, which is that the transition we most care about, the one that is protected from relaxation, you see doesn't actually show up. If I circle this dotted line here, that's really our transition that we care about. And you might say, like, oh no, the transition we want doesn't show up, but that's actually a good sign, because that matrix element is really small, which means you can't drive directly from the 0 state to the 1 state. You have to sort of do something more complicated. And so in order to do this, we actually wind up driving a Raman transition, or at least in this first work, we drove a Raman transition. So we drive, virtually up to some higher level that's shared between the wells, and then back down in order to do the control of the system. And if you do that, then you can actually map out this avoided crossing that shows that you have a first order insensitive point in flux for this one transition. And so it is completely, or it is very heavily protected against relaxation. You can't get T1 effects, and you have at least first order protection against flux. So this isn't as good as you could get in principle. And if we make the coherence larger, then if you make the inductance larger, you could get this to flatten out just like we did with the transmon and get something that really is robust to all orders. But it's a thing that at least gives us a good degree of protection. Okay, and this is really the first qubit that has both disjoint levels, so it has intrinsic T1 protection and first order T2 protection. So it's a fundamentally new kind of device. If we measure the coherence, T1 is now up to 1.5 milliseconds, and T2 can be about 25 microseconds. And so we can see that we're not as good as the best transmons yet in terms of T2, but T1 is actually much better than the best transmons. And there's no other device that has this combination of T1 and T2. Now, interestingly, if you just want to build a computer out of this device, if all you want is to build like a computer that's like 1 million 0-pi devices, then the number you care about is this T2 number, and it's not as good as transmons, though it hasn't had a decade or more of development to make it that good. but even if that's even if you sort of take this at face value, it's already really quite good. Because it turns out there's other architectures for doing quantum computing besides like building lots and lots of qubits. And it's a technique that's really been pioneered at Yale, trying to use the qubits not actually to store information, but to control information in cavities. And if you have a device like this available, where T1 is really long and T2 is okay, then that actually turns out to be particularly useful for that architecture. And so these are the kinds of ideas we're going to explore in terms of co-design in this center, where instead of just saying, here's this one metric and we have to live by this one metric, we are trying to think about how this device could be useful and dovetail with the architectures developed in other parts of the center. And by working collectively and using different people's expertise, I think we can do quite a bit more than we've been able to do. Okay, I'm a big fan of this sort of intrinsic protection against relaxation story, because it mirrors what happened with the development of a transmon, and that's what I did in Rob Sholkoff's lab as a postdoc, and so it felt like my life like repeating over and over again. But there's a second approach, which is if you want to make these relaxation times long, you can sort of, instead of just trying to engineer the matrix element, you can actually in principle figure out like what's going on in the material side of things, and look at the materials. And so this is what we've been doing in another half of our group, in a couple of collaborations. I'm gonna be talking about one that I did with Natalie De Leon at Princeton and Bob Cava at Princeton. But what we're really hoping to do as we move into the center is work with the fantastic beamline scientists at Brookhaven National Lab. I did some collaboration with Inyas Nyarig, and we started looking at niobium and the fundamental defects there, and moving forward into the center, this is the kind of thing that matters. Okay, so what's been known for a long time in the field is that most of our loss in the qubits comes from something that's going on at a surface somewhere. And the way you know this is by making this plot that Chen Wang made in Rob Sholkoff's group. Chen is now a professor who's part of our center, as is Rob. And what you can do is you can sort of take a transmon and you can essentially move the two sides of the capacitor further and further and further apart. And if you think about where the electric field goes, as the capacitor pads get further and further apart, the electric field penetrates deeper and deeper into the substrate, and you are less and less sensitive to things at surfaces. And if less of your electric field is in the surface, then your T1 goes up, because you're affected by how lossy a material that you might have is, and how much of your electric field is in that material. And so as you make the capacitors further and further apart, your coherence goes up and up and up, and life is great. And so this tells us that something is wrong at the surface. And so Natalie De Leon and I were sort of talking to Bob Cava, who is a chemistry professor at Princeton, and he said, well, obviously your surfaces are bad because you're using niobium, and niobium is, this terrible, terrible material. And he spent some time in the 80s and 90s, and had sort of studied niobium oxides, and there's like all of these different nioxides and niobium oxides, and some of them are conducting, and some are insulating, and some do like terrible things. And so he's like, you're not going to get consistent results with niobium. Why don't you try tantalum? And so we went back to our lab and decided, okay, let's try tantalum. And it's not just tantalum. So it took one other piece of information that we happen to have. So if you just deposit a thin film of tantalum, it forms in a different crystal phase in thin film than it does in bulk. And that thin film phase has a much lower critical temperature, and it doesn't actually work very well. But if you either deposit it hot, or if you use a niobium seed layer, and in our case, we deposit it hot, then you can get it to form a body-centered cubic phase that has a TC that's about 5 Kelvin, and the growth turns out to be really miraculously good. We get growth up in crystalline columns all the way from the substrate up to the surface. the grain size is on the order of 5 to 10 nanometers. And if you sort of grow this material really nicely and process it well, things are good. You can also sort of look, these are the atoms at the interface of the metal and the sapphire, and you can see that the interface is incredibly clean, and that the tantalum atoms line on top of the oxygen atoms in the sapphire substrate. And so you can really just show that like this winds up being visually a really nice material. And if you measure coherence, and if you learn to process it well, then you can see coherence times that are sort of something around 1/3 of a millisecond for some of our very best devices, and pretty consistently above 200 microseconds, which is sort of record levels of coherence for transmon qubits, by essentially trying not to make the qubits themselves immune to noise, but by trying to understand what are the origins of noise, either by sort of changing parameters of the device design to infer where the problem is, or by talking to people who know about material science to actually isolate the microscopic origin of noise. And this is sort of our launching off point for the C2QA work, where we're really now bringing in a whole bunch of really just amazing material scientists who know how to think about materials, how to analyze materials, how to understand materials, and how to grow pure materials in order to actually improve coherence times through materials engineering. And these add together, right? So we've now made our 0 pi device out of tantalum materials, and you sort of see in a lot of ways these gains can in fact multiply. And so these are the kinds of things we're going to be exploring in the center. And I'm going to stop here, but it's really trying to sort of combine materials and device engineering in a variety of ways in order to show these kinds of gains in qubit coherence. And I've given you some examples today of the device approach and the materials approach. In the coming weeks, you'll hear from the thrust leaders of the 3 big areas to talk about sort of broadly materials issues in quantum devices, broadly interesting devices and applications and software that are being developed. And then after that, we'll have a series of talks from people in the center who will dig really into detail about particularly exciting results that are coming up through the pipe. So thanks for your attention.
Thank you very much, Andrew. And for those who have questions, please use the chat box or the raise hand feature.
All right, we have one question already from Vladimir.
So was your question more about setting it up or evaluating the integral?
I'm Vladimir. Can I ask a question? I'm Vladimir. Can I ask a question?
Yep.
Okay, so qubits decohere, and how many gates can you perform before qubit will decohere?
Yeah, right. So I think, I mean, that's sort of the interesting question, right? So so in our very first version, so I'd say in a transmon, a typical single qubit gate takes sort of on the order of 10 or 20 nanoseconds and so you can perform something like 10 to the 4 single qubit gates. 2 qubits gates tend to be slower depending on your approach. And it really does depend on your approach. If you used fixed frequency qubits that can't be tuned, then the 2 qubit gates tend to be slower and they tend to take 100 or 200 nanoseconds. If you use tunable qubits, the gates can be faster, but your coherence times are lower. So it's something like 10 to the 4 single qubit gates, and 10 to the 3 or a few hundred single 2 qubit gates. In the 0 pi device we made, our gates were much slower because we had to use these Raman transitions in the earlier version. Actually, in our recent data, we figured out how to make those transitions quite a bit faster. So I would say you can do there is sometimes a trade-off between the speed of gates, but we've now actually made some of the 0 pi gates quite a bit faster. In the cavity-based qubits, the operations tend to be a fair bit slower, but the coherence times are incredibly long. And so those are the ones that are sort of right around where they're breaking even in error correction. And so if you can sort of find a novel qubit that serves the role for the cavity-based quantum information in terms of doing those manipulations well, then suddenly you could be well over a threshold and do all sorts of interesting things.
Thank you.
There seems to be no other questions on the raise hand. I just want to remind everybody that the raise hand button is under the participant button on the lower right corner. All right, we have the next question from Tom Delord. Feel free to unmute yourself.
Yeah, it's a short question. At the end, you talked about coherence time, but you showed T1 curve. Is that because you assume you can get the T2 as far as the T1?
Yeah. So in fixed frequency transmons, the limit has really been T1. And so we've been pushing, we've been really sort of benchmarking those by T1. The T2s we can get with echo are often sort of up to like 200 microseconds, so not quite 2 T1. If we do dynamical decoupling, we can bring that up to 2 T1.
Thank you.
Carl, do you have a question in the chat?
Yeah, so I see someone in the chat asked, what do I envision the post-NISQ era will look like? That's a great question. I mean, I would say, right now in the NISQ era, there's a lot of really exciting things happening, but there's also a lot of evidence that some of these NISQ algorithms can be easily simulated. In the post-NISQ era, we'll really have these fault-tolerant devices where you can actually do error correction and start to think of doing logical operations. But to get there, we need qubits that have longer coherence. They can have faster operation. You can couple more of them together. You can have bigger systems that you can really do these error correction operations, right? You're going to have, depending on how you do it, an enormous amount of infrastructure dedicated to just doing the error correction, the classical computing and control part of that error correction, in order to finally eke out some actual quantum advantage on some useful problem. But that's why it's a real center-wide effort, because we need innovation and breakthroughs at almost every level of all of that. So there's really a lot to be done, but also a lot of progress has been made in the last decade.
Sal, any raised hands?
Yep, there are Maverick James just raised his hand.
Yeah, so I was wondering what the entanglement process looks like for superconducting qubits.
Yeah, so the entanglement process, essentially you need something to mediate an interaction between the qubits, and so very often you put some third object between a pair of transmons, and so there's sort of two ways you can do it. So the IBM approach, if I'm thinking about industry approaches, is to put a resonator, just a linear resonator in between them, and everything is fixed in frequency. But if you apply microwave pulses at just the right frequencies and intensities, then you can sort of drive a transition that sort of forces entanglement to be generated. In the Google approach, what they do is they actually have, the thing that's between two transmons is yet another transmon, yet another qubit, and they like those because they're tunable and they can bring it into and out of resonance with the devices, and that allows them to do gates that are sort of much quicker. They can sort of push levels around by like tuning this knob in between. But essentially, what you're doing is you're essentially creating interaction between various states, sort of mediated by photons that are exchanged through some object.
At this
Okay,
time,
thank you.
At this time, I would like to just thank you very much, Andrew, on behalf of all of the participants for giving us this in-depth lecture about C2QA and the research that you're doing. And I'd also like to give up an ad right now for next week's Quantum Thursday, where we have Dr. Nathan Weeb, who is the lead of the software thrust at the center, and his talk will be entitled New Methods for Simulating Quantum Dynamics. I hope you all could join us next week, Thursday at 1 p.m. And I want each and every one of you all to also advertise this Quantum Thursday lecture series to your colleagues so we all can join and understand as we move forward in overcoming the noise. Thank you very much, Andrew. Thank you very much, everyone.